Today's session we are going to see about assemblers. So that's our unit 2. Assemblers, what is mean by an assembler? We all know that assembler is a system software which helps us to convert the assembly language program into machine language code. So usually the machine language code is called as object code. So assembler will convert the assembly coding to object code, whereas our compiler will convert our higher level language into object code. So in our complete unit, we are going to see how an assembler convert an assembly language program into an object code. So in case of static memory, how it will convert, in case of multi-programming, how it generates an object code. So that is we are going to see in our complete unit. So first topic, introduction about assembler. Role of a assembler. So an assembler, when a source program is given to an assembler, it will convert that source program to an object code. So that is the main function of our assembler. So this object code is given to our linker. So linker will link all the needed files for a program, and then it creates an exe file, executable code file. So this exe file will be again given to the loader. So our loader will load the program in memory for execution. So this is the complete processing of a conversion of a program to a object program, and from the object program how an execution is done and how an output is generated. So this is the complete processing. So the fundamental function, of our assembler is translating assembly coding, that is mnemonic codes, to machine language equivalents. So this is the primary function of our assembler. Then it also assigns machine addresses to the symbolic labels. So symbolic labels is nothing but the user defined variables are called as labels. So it assigns the addresses to the user defined labels. Usually the addresses will be stored, that the label once created by a user will be stored in memory using a symbol table. So symbol table is a table which contain the details about the symbolic labels. So our assembler will create a symbol table and add the labels inside the symbol table, and it also assign the addresses. The value that is present inside the labels is also represented inside symbol table. So this is the major function of our assembler. So in an assembly language program is nothing but it is like mnemonic codes. So in assembly language program there are some pseudo instructions. So this pseudo instructions are nothing but they are our assembler directives. So these assembler directives, these pseudo instructions are not translated into machine instructions. It is meant for performing some functions of the assembler, that is it provide information to the assembler. So that is the main purpose of our assembler directives. So the instructions containing assembler directives will not be converted to object code. So now a lot of assembler directives are available. Now in basic we will be going to study about the first 6 assembler directives. So first assembler directive, start. So start, the purpose of start assembler directive is it specifies the name of the program and starting address of the program. So this is the function of start assembler directive. Then end. So end assembler directive will indicate the end of the program. So for indicating the end of the program, we will use end assembler directive, and optionally it may also contain the address of the first executable instruction. Next assembler directive is byte. So byte assembler directive, it helps to generate a character or hexadecimal constant. Character or hexadecimal constant. So next assembler directive is word. So our byte will generate character or hexadecimal constant, whereas our word will generate one word integer constant. Next assembler directive is RESB. RESB stands for reserved bytes. So it reserves the indicated number of bytes for a data area. Then RESW. RESW stands for reserved word. So like a reserved byte, reserved word will reserve the indicated number of words for a data area. So these are the basic assembler directives that is available in all assembly language coding: start, end, byte, word, RESB and RESW. Now let us see an example program. Example SIC program. So our example SIC program will be written like this only. So first there will be line, then LOC, location counter, then our source statement will be there, and then finally object code. So this object code will be generated by the assemblers. So the line numbers will be 5, 10, 15, 20, 25 likewise, and the location counter starts with the value specified in the start assembler directive. So for example, copy is the name of my program. So start is our assembler directive. It will specify the name of the program and also the starting address. So this is the starting address where our program has to get loaded in the memory. So next instruction is first STLRETADR. So this is the next instruction. Next 1003 C loop J sub RD REC. So an object code will be generated for each and every instruction. Next LDA length COMP 0. So this is our example program. So like this is our sample SIC program. So start is our assembler directive. So this start assembler directive will specify the name of our program is copy, then the starting address is 1000. So the 1000 will be the location of our program in memory. So from 1000 the program has get started, 1000, 1003, 1004, 1005, like this each and every instructions will be saved in the memory. So this is the next instruction. So in our SIC program, this column, 3 columns will be the first column will be our label part, second will be our opcode, and third will be our operands. So this is our object code that is already specified. This is our location counter value that is also already specified. So we have to separate the source statement into 3 columns. First will be label, next opcode, finally operand. So now let us discuss about the assembler functions. So assembler functions, the major function of assembler is translating the source program to object code. So while translating the source program to object code, it requires the following function. First, it will convert mnemonic operation codes to their machine language equivalents. For example, in our is it our example program? First STLRETADR. So this is the first line of our program. So here I already told this is our label part, and this is our opcode part, and this is operand part. So while converting the source program to object code, it will first convert the mnemonic operation codes. Operation codes is nothing but the opcodes. So this STL is an opcode. So this will be converted to their machine language equivalent. So the opcode value for our operation code STL is 14. So this is already predefined. So we have a complete list of the numbers for each and every opcode individually for SIC and SIC-XC program. So the value for the opcodes is already predefined. So it will first convert the opcodes to their machine language equivalents. Since we cannot understand the machine language code. Machine language code is completely binary, zeros and ones. So we cannot understand the machine level language codings. So in our complete syllabus, we will be discussing only in hexadecimal value. Because of easier understanding, we are saying everything in hexadecimal value. So the machine language equivalent for the opcode STL is 14. So that is the first function. Next, it convert symbolic operands to their equivalent machine addresses. Equivalent machine addresses. So symbolic operand. So this is our operand field. So this symbolic operands will be converted to their equivalent machine addresses. So in our program, so this is the operand. The operand will be present in some other addresses. For example, let us take RETADR is present in the address 1033. So RETADR is nothing but it is a reserved word. So it will convert this operand to their equivalent machine addresses. The machine address for RETADR is 1033. So it will convert RETADR to 1033. Okay. So this is the final object code of this particular line. First it will convert the mnemonic opcodes to their equivalent. So the mnemonic opcode for STL is 14. Then it will convert the symbolic operands to their machine addresses. So RET ADR is present in the address 1033. So it converts to their equivalent address 1033. So it will club up these two things, the opcode value and the operand address, and it will form the object code in SIC program. SIC supports only two addressing mode, direct and indexed addressing mode. So it will be very easier in forming the object code. Whereas in SIC XC we are having many addressing modes, so the formation of object code will be somewhat indirect manner. So we will discuss about this in the later sessions. Next function, build machine instructions in proper format. Yes, it will build the machine instructions in proper format. Then it convert the data constants specified in the source program to their internal representation, internal machine representation. For example, if a machine constant, if a constant is given EOF byte, character is it. So byte is an assembler directive. What is the function of byte? Byte will generate a character or hexadecimal constant. C denotes character constant. So it has generated a character constant Z. So what is the ASCII value of Z? Capital Z, it is 90. So our assembler function will also convert the data constants to their internal machine representations. Next. Finally, after forming all the object codes, it will write the object program and assembly listing. So this is the 5 major functions of assembler: converting opcode to their equivalents, machine equivalents, converting symbolic operands to their equivalent addresses. Then if some constants are present, it will convert them to their machine equivalents. Then it will build the instructions in a proper format. Then it finally, after generating the object code, it will write the object program and assembly listing. So these are the functions, major functions of assemblers. So all these functions, that is converting mnemonic operation codes into machine equivalents, building machine instructions in proper format, convert data constants, writing the object program, everything can be accomplished at a single processing. While an assembler reads a line, after reading a line, for example, if it read this line, so it will look at the opcode, it will convert it. Okay, so these functions can be done in a single pass, except the function number 2, that is converting symbolic operands to equivalent machine addresses. So let us consider that our assembler is reading this particular line. So the first function is converting the opcodes, operation codes to their machine equivalent. So STL is converted to 14. Then it reads the symbolic operand RET ADR. While reading this particular line, the assembler does not know where this operand, symbolic operand, is present in the program, because the reference to this RET ADR operand is present later in the program. It may be in some 90th line or 100th line, but whereas this is our first line. So while reading the first line, our assembler don't know where this RET ADR is present, because the reference to this symbolic operand is made later in the program. So this problem is called as forward reference problem. Can you understand what is meant by forward reference? That is, the reference to a label, reference to an operand is made later in the program. While reading that particular line, we don't know where that RETDR is present, because we have just reading only this first line, whereas RETDR, the actual definition of RETDR is present somewhere in the 100th line. So we don't know where this particular RETDR is defined. So this problem is called as forward reference. Because of this forward reference problem only, our assembler cannot convert the source program to our object program in a single pass. It will take 2 passes. Passes is nothing but 2 scanning of our program. So in the first pass, it will scan complete program. Then whatever function it needs to do, it will do that function. Then the functions that cannot be accomplished in the first pass will be done in the second pass. After completion of second pass, we will generate an object code. Now let us see about the object program. Assembler write the generated object code. So this is the object code. So it will write the generated object code in some output device. Object program will be loaded into the memory later on for execution. So in object program, there are 3 main records. Lot of records are there. We will discuss one by one. But basically there are 3 records: header record, text record, and end record. So header record will contains the program name, starting address, and length. Text record will contain the translated instructions and data of the program together with an indication of addresses where these are to be loaded. Then end record will mark the end of the program and specifies the address in the program where execution is to begin. So these are the major functions of these 3 records. Now let us discuss about how these records will be formed. For header record, column 1 will contain H. Column 2 to 7 will contain program name. Column 8 to 13 will contain starting address of the object program. So everything we will be representing in hexadecimal. Then column 14 to 19 will contain length of object program. So this is the format of our header record. Next, text record. So in text record, column 1 will contain T and column 2 to 7 will contain starting address. So starting address of object code in this record. Then column 8 to 9 will contain length of object code in this record. So in a particular text record, we can store up to 10 object codes at a maximum level. So after storing 10 object codes, we will write the next text record. So the starting address of that particular object code in that particular record, then the length of the object code that is stored in a particular text record will be specified in columns 2 to 7 and 8 to 9. Then column 10 to 69 will contain the object codes, actual object codes. So this is about text record. Then end record. So in end record, column 1 will contain E and column 2 to 7 will contain address of first executable instruction. So this is the format of our object program. So now let us see an example object program for an SIC program that we have seen before. H, column 1 will contains H, then copy is the name of the program, column 2 to 7, 2, 3, 4, 5, 6, 7. Then starting address, so our starting address is specified in the start. So in start we have specified 1000 as a starting address, so 00 1000. Then length, so complete length. Length will be calculated by subtracting the lost value. Finally, we will have an end record location counter value in the end record. We have to subtract that final value with the starting address. That will give the complete length of our program. So the length of the program that we have taken is 107A. Next, text record will start with T. Then column 2 to 7 will contain the starting address. So first starting address of the object code will be in this address only, so you have to write that address. Next we have to specify the length of the object code. For example, if we are having so these are an example object codes, so I am writing an example as an example. Okay, so in this particular text record I am storing how many object codes? 1, 2, 3, 4 object codes. So each object code is of 3 bytes. 3 bytes. So totally 4 object codes are there. So 4 into 3 equal to 12 bytes. So what is the hexadecimal value for 12? For 10 it is A, for 11 it is B, for 12 it is C. So 12 is represented as 0C. So the length of a text record is 0C. So if I am storing 7 records, 7 object codes means the length will be 3 into 7 is equal to 21. You have to convert the 21 into hexadecimal and represent here. Then next text record. So in the text record at a maximum we can store only 10 object codes. Keep it in mind. So after 10 object codes is completed, you have to represent it in the next text record. So the next text record will start with the place where this object code ends. So the next object code will start at some other position that will be represented in location counter value. That object code you have to write here. For example, if the next object code is 002039, you have to mention here. Mention that starting address of the object code. Then the object codes. Then how many object codes we are writing? How to find the length and represent here. Find the end record. In end record, column 1 is marked with E. Then column 2 to 7 will mark the address of the first executable instruction. So the address of the first executable instruction is nothing but our 1000. So you have to represent here. So this is our model object program. Hope you understand about the various functions performed by the assemblers, and we have seen a sample program how machine code is generated from a assembly language program. And what is the final output? The final output is our object program and the format of the object program. How many records will be there? We have seen the format with an example. So in the next class, we will see about the passes, that is 2-pass assembler. So already we have seen that assemblers cannot convert a source program into object code in a single pass. It will take 2 passes due to the presence of forward reference problem. So 2 passes, in the first pass we will scan the program and assign addresses to all the symbolic labels, and in the second pass only the actual formation of the object code and writing of object program will be done. So we will discuss in detail about pass 1 of a 2 pass assembler and pass 2 of a 2 pass assembler in our next class. Thank you.